Hello, everybody. So I will speak about the truncated moment problem, and I will speak about three special topics: the covariety and the set of atoms, anchor matrices, and maximal masses. I will not speak about existence problems and the flat extension theorem, and I will not touch the existence problem, because I believe that there are no reasonable, easily verified criteria. So I study the structure of moment functionals and of the moment cone. So after formulation of the moment problem, I will have a section on the covariety, then I will have a section on anchor matrices, as many well-known things, and a few new things, and then I will speak about maximal masses. Just let me first review the general setup. X is a locally compact Hausdorff space. We may think RD. K is a closed subset. We may think of a semi-Frank subset. A is a finite dimensional linear subspace of the continuous functions. And sans serif A is a sequence of basis elements of this vector space. So we may think here of polynomials. A are polynomials, say up to the degree 2n, and here just some monomials. But this first part works in a very general setup. We don't need polynomials here. And I will assume always that there is one function which is larger or equal 1. We may take the function of polynomial 1. So then there's a well-known correspondence between these functionals and sequences of m real numbers, just by L as basis elements is Si. So it's a given real sequence associated to the basis elements. And then the truncated K moment problem is what I have here written. Does there exist a Radon measure mu on X such that the port is contained in K and Si are the moments, the integrals with respect to the measure of the basis elements AI, or the functional is an integral over point evaluations with respect to the measure. This is a general setup, and if this is true, then it's called a truncated K moment functional. Mu is a representing measure, and in the general case of K is equal to X, I would just speak simple about the moment functional. It has a very interesting history. The moment this moment problem, it goes back to Gauss, Jacobi, and Christoffel in dimension 1. They worked with quadrature formulas. The case 1, the truncated moment problem in polynomials for 1 to x up to n, without gaps, was in principle settled by Archieso and Crane in a paper in 38 last century, and translated by the MS, and another one by Crane alone in 51. These are very large papers, almost books, dealing with the one-dimensional case and solving it. Then, interesting enough, there was in the 60s, 70s, papers dealing with general functions by Kemperman, Starling, and others. The polynomial case came only, multidimensional polynomial case came only very late. The first one was a thesis by John Matzke in 92. It was not published. It contained a number of results that appeared later in papers. And then, starting in 96, Raul Couto and Larry Fialkov in a large number of papers, and since the last years. My talk is based on two papers, partly on two papers with Philippe de Dio from 2018, and another paper in 2015. So most of all the theorems are contained in my credit text book. Not so a talk, but at least the theorems are there. So the most important theorem for the truncated moment problem, called fundamental theorem, it's what I called Richter-Chakalov theorem. It's the following result. Suppose we have a measure space and a finite dimensional subspace of mu integrable functions, real functions, and then the integral of f d mu over x can be given by an atomic measure. Then there is a k atomic measure. K is less or equal to the dimension of V, such that the integral with respect to mu is equal to the integral with respect to mu. This is computed to be this, so we have just a linear combination of point evaluations. It is appeared in a strange journal, Blätter der Deutschen Gesellschaft für Versicherungsmathematik, 57, and at the same time by Tcherkalov in the Bulletin, the French Bulletin. And this contains only a very special case. It's not it doesn't work in the compact case. And the interesting thing is we in a paper with Philippe Didier, with the moment Cohen, we looked at the history of this theorem from 39 to 2006. I mean, it's more thrill than any Hitchcock movie. So going back and results is very interesting. But finally, the result is contained in Richter's paper, and that's why it might be fair to call it Richter's theorem. As a consequence, we have each truncated k-moment functional has a k-atomic representing measure, and the atoms are all in k, and k is less or equal dimension of A. So in particular, there's a nice sharpening of this result. If we have a representing measure mu, and we have a null set, then the atoms can be chosen outside of this null set. So in particular, if we have Lebesgue density, and then we can take zero-dimensional curves, and we can avoid that the measures are in certain curves or certain points. So the Richter-Tcherkalov theorem says each moment functional is a linear, finite linear, non-negative combination of point evaluations. This result is also important from the theory is behind the moment problem. It brings convex analysis into the game, and it is now, I believe, after real algebra, the most important technical tool for studying such moment problems. Let me come to the first section, covariety. If we have a moment functional L, then we define the set of atoms, WL, all points in the set X, such that the singleton is a set consisting only of X, has a positive measure. So this is an atom of the representing measure, and we take now all atoms for all representing measures WL. And a priori it's not clear that this set is closed or how to describe it and what can be said about this. And the outcome of the section is it's a very nice set. It's in the case of polynomials a real algebraic set. And the idea is also very simple. If we take a positive measure and then a negative polynomial on the support, and if the integral is 0, then it's clear that the support of the measure is contained in the 0 set of the polynomial. It's very easy if we take a point which is not in the 0 set, then the polynomial is in the small neighborhood, larger or equal to epsilon. Because it's non-negative, this cannot cancel. If it is 0, contradiction. So, if it's not in the support, then we obtain a contradiction. And this simple idea is used several times and is built in the notion of the covariety, which was invented by Larry Fialkov in 2015. And this is the iterating of this procedure. Let's define the set N1 of L. We take all positive polynomials on the whole set, V0 is X, on the whole set, and which are annihilated by the moment functional. And then we take the set V1L, all points which are annihilated by this N1L. Then the support of each representing measure is contained in V1L by this remark. But it turns out that it's not each point is of the 0 set is a support, is an atom of a representing measure. Because of this, we iterate the procedure. Now we take N2L, all polynomials which are annihilated by the moment functional. So this is not changed, but we take polynomials which are non-negative on this smaller set, V1L, not on the whole X, on a smaller set. The larger quantity, so we get and then we take the 0 set of this set N2L. This is V2L. And we continue this, and the sets become smaller and smaller, and the intersection is a covariety. in the simple case, we take just a k-atomic measure and the integral over it. Then n1 of L is just a set of all polynomials up to degree 2n, which are negative on Rd, which are vanishing at these k points. And V1 of L is a zero set of this set of polynomials. So these are zeros of polynomials. All sets V sub k are zeros of real polynomials, and so we have real algebraic sets in the polynomial case. But the results work in general case for continuous function as well. Now, two basic things. I said it already. If n the index becomes larger, then the set becomes smaller because the positive this set there are more positive polynomials on the smaller set. So this nk becomes larger, vk becomes smaller. And there's a number where it stabilizes. This follows from convex analysis, and we shown this. And each representing measure is supported on VL. An important point is also what can be said about a given moment functional. What can be said about the smallest m, where this whole thing stabilizes. And first, let me know the simplest example where V1 is equal, V1L is different from the covariety. So we need to go to step 2. And this polynomial, this example we had is a polynomial with gaps, x up to 3 is missing. And we take just a very simple example of an atomic measure at atoms at -1, +1, and 2. And then it can be shown that V1 of L are these 4 points, 1, -1, 2, and -2. And V2 is 1, -1, 1, 2. And the reason is because x up to 3 is missing, the positive polynomials which are vanishing at these 3 points, are all of them are multiple of this. There are no others because then x up to 3 would be needed. And getting this, we get a smaller covariety. In our paper with Philippe Didio, we were searching for polynomials without gaps, and we didn't succeed. And even a Robinson polynomial was not an example we could take. But later, after publishing this paper, we discovered that there is another polynomial, the negative polynomial, degree 10, Harris polynomial. And if we place, there's 30 zeros. We need, for counterexamples, we need positive polynomials with many zeros. And for this polynomial, we could show that if we place atoms at the zeros, we get also that V1 is different from V2. And concerning the M, the question is, of course, natural. When is V1L? It's VL. So we need only one step. And for inner points, this is true because V1L is just X. This is easily seen. But for boundary points, it's not clear. And for boundary points, it's V1 of L is V of L if and only if L belongs to the relative interior of an exposed face. Exposed face are zeros of polynomials, or they lie in a supporting hyperplane. So if it's an interior of an exposed face, then we have V1, and probably it's true for M. If we then go to the boundary of an exposed face and step by step. But in our paper, we have only this. And now, 3 basis results on the covariety. So, the first one is, was a main motivation for me to look at this. For each truncated mode functional, the covariety is the set of atoms. So in particular, the set of atoms is closed. It's a very nice set. We have continuous functions. That's why 0 sets of continuous functions are closed. And if you have polynomials, these are real algebraic sets. The set of atoms, all possible atoms, are real algebraic sets. The second result is the measure is unique, as a unique representing measure, if and only if we take all vectors, an to a m must be an m here, and x is running through a covariety, and if this set of vectors is linear independent. So if you have many points, then it's not independent, and precisely the covariety gives the result when it's true. And there's another result by Fialkov and Breckermann. Is also a very nice result. Suppose we have a general linear functional. In my talk, all functionals, most of them are moment functionals. But if you have a general functional, this makes sense as well, the covariety. And if we have a functional which is at this unique element 1 positive, then it's a moment functional if and only if the covariety is not empty. So this is a nice theoretical characterization of moment functionals, covariety non-empty, we have a moment functional. And in this case, then the supporting measures are all contained in the covariety. So this shows that the covariety is a very central object for truncated moment problems, and it is in some sense the first end of a story. Coming to the next point, Hanker matrices. This is a subject that probably most of you know very well. Let me switch now to polynomials. We take a set of monomials x up to alpha from Zn, and the linear span. And now we consider linear functionals which are on a squared, the linear span of products, not of a squared. And this has an advantage. And if you have general sets A, point evaluations are not in general do not span extreme rays. But for a squared, the extreme rays are of the moment cone, L is the cone of moment functionals, are precisely the multiples of point evaluations. This fits nicely into the theory that point evaluation should be extremal objects. And this is true for a squared. And then we define the Hanker matrix. The functional at Lx plus alpha beta is the entry H alpha beta. And this we plug in a matrix and we get the n cross n matrix, the metric matrix, the Hanker matrix. This is often called also the moment problem by Bernard and other people. I avoid this because it's true we can do this for any functional, and even if the function is only positive, without having a moment, a measure behind. And two important quantities are zero sets, the kernel of this functional. These are all f's in A, such that LF times G is 0 for all G. And then the zero set of this n sub L is V sub L. It's a variety associated with L. So L is a function on L squared. Now some other basic results, they are very easy properties. We fix an ordering of the index set, and then we can write each polynomial in A as a real linear combination of x up to alpha, and we take the coefficient vector and write it as a column according to the ordering, and then we have this well-known formula. L times G is the matrix multiplied by the coefficients of f and g, the coefficient vectors. So all computations of the functional can be reduced to Hanker matrices. So we can avoid completely the functional here and play the game of Hanker matrices. An element belongs to the kernel if and only if the vector belongs to the kernel of the matrix. The dimensions are equal. Also, positivity is very nicely reformulated. F squared is non-negative for f and a, if and only if the Hanker matrix is positive semi-definite. In particular, in this case, the kernel are just all squares which are annihilated. This is a very important point. Hanker matrices and these kernel reach only squares of elements. In contrast to the covariety where we take positive elements. This is a drawback of Hanker matrix method. We're dealing with functionals on a squared, say if the polynomials are 2n, and a are the polynomials to n only. So f squared makes sense, but you cannot square multiply higher because it stops at a squared. So the fourth condition is also, assertion is also useful. Support of each representing measure is contained in this V sub L. This variety and this kernel was introduced in the first papers by Koto and Vyalkov in the end of 90s. Other remarks on the Hanker matrices. So the Hanker matrix, if it is suppose the function is positive on a squared, this means LF squared is non-negative for all f in A. This is the general assumption. It does not imply moment functional, we know, but it's a general useful condition to study the Hanker matrix. In this case, one can form a GNS-like construction. We take the kernel or the zeros of squares, and then we take the quotient A up to NL and define an inner product in this manner. And then if the Hanker matrix has a finite rank, in particular if the set n is finite, it's not assumed here, then it's a finite dimensional real Hilbert space, and we can apply methods from Hilbert space theory. This is a GNS-like construction. There is a drawback. We cannot, in the multidimensional full moment case, we can multiply polynomials and let the polynomial act. This is not true in general here, because if we multiply f by other polynomials in action, then we come out of a squared if the degrees are too high, and the functional does not apply. But nevertheless, we have a Hilbert space and can apply theory. Let me compare this to the covariety. Of course, the covariety is contained in this set. This is, roughly speaking, the set of squares, zeros annihilated or squares which are annihilated by L, and while the covariety has non-negative polynomials. And the contrast is could be very sharp. It's possible that NL is only 0 element and VL is RD. But the functional has a unique representing measure with a fine set of atoms. For instance, if we take atoms, place atoms at the zeros of the Robinson polynomial, it has this property. So the covariety is very different from this Hanker variety. And in this case, the Hanker matrix method is not really useful. So it's useful if we have small number of atoms. For a large number is not possible. Maybe I skip this in order to be in time. There are fine points in the zero set, just one remark, which distinguishes positive polynomials from truncated moment functionals. The product is inside it if PQ is in A for positive functionals, and for truncated moment functionals, PQA is in A. And for positive functional, we need a stronger condition. Let me skip this. Let me come to Hanker matrices of concrete measures. We take a finitely atomic measure, and it could be signed measure. The numbers here are not necessarily positive, and take the corresponding linear functional defined by the integral over this measure or the linear combination of the point evaluation. And then there's this important quantity. The rank of HL is less or equal K. It's less or equal, of course, to the number of points in V sub L. And this, in general, it's not true, the equality. And the important point when the rank is K, this is not difficult to show, that is if and only if the point evaluations x1 to xk considered as functionals on A, not on A squared, on A only, are linear independent. In this case, we have equality here, and this is a very important point for when this happens. And such functionals, I called it minimal, if the rank of the Hanker matrix is equal to the number of points in the variety V sub L. And let me assume now that we have finite set n, so finite dimensional space. These are very nice objects. Unfortunately, this is a very certain case. And in this proposition says if we have a minimal functional, then it's determinate, the representing measure, unique representing measure is rank HL atomic, and we can compute the masses at m1 to mk, at the points x1 to xk, by taking the inverse of this matrix, applying this to this vector. So everything is fine for minimal functionals. Roughly speaking, minimal is slightly simplified, is if squares are enough to deal with this, because we have here the zero set. V sub L is defined by all elements which are vanishing at the kernel, and the kernel are those which are vanishing at L, where the squares are vanishing. So the minimal functionals have a flavor that sums of squares are enough to deal with it. Of course, there are many examples where this is not, which are not minimal, and the simplest example is this one. We take n points from Rn, from R, and form a polynomial in x1, and the same n different points from x2, and we place an n squared atomic measure and at these points with coordinates alpha I, beta j, n squared, and then one can compute that the rank is n over 2, n plus 2 over 2 minus 2. The difference of the Hanke variety minus rank is n minus 1 over 2. So it becomes large if the degree becomes large in two variables. This functional is determinate even, but it's not minimal. So the minimal is a very seldom case, the best possible one. I will come later to give another advantage of minimal. Let's come now to the third part of this talk, maximal masses. And I will take x equal Rd and a finite subset of n0d and a set of monomials x up to alpha finite set and the linear span. So these are multidimensional polynomials, but they may have gaps because n is not we have not all polynomials up to degree 2n. And A plus is all elements which are non-negative and k. And let L denote the cone of truncated k moment functionals. This is a basic object here, the cone of all moment functionals. And L of lower x is the point evaluation, L of xp is p of x, p and a. So there are three important numbers defined here. And in the next slide, I will show that they're all equal if the set is compact. And they have all meaning for another look at the point. We have a point and the moment functional. And here we look for the supremum of all negative numbers, such that moment functional times c point evaluation is in the moment cone. So this is just, if we subtract, we have a moment functional inside or on the boundary of the moment cone, and we subtract multiples of fixed point evaluation. And if we become larger and larger, then we touch the boundary, and supremum of all such c's is the largest point that we touch the boundary. So this is written here. It is not, in general, it's not attained. So L minus CL is not necessarily a moment functional. The second one is well-known problem from optimization. We're looking for the infimum of a linear functional, L of p, L is fixed, over a cone or positive or negative polynomials, and a constraint, another function is equal to 1. This is kappa Lx. And the third quantity is we take the supremum of all masses for all at the point of the point x for all representing measures. So this is a maximal mass. Maximal is a bit confusing here because it's the supremum. It's also not, in general, not necessarily attained in the moment. So these are three different important quantities, and they are closely related. If we have a moment functional and a point, then we have this inequality. Rho of L is equal CL, is less or equal kappa, and they're all finite. And in the compact case, they are all equal. And in this case, the moment cone is closed, so we can supremum here, the largest number. If we subtract this, then it is a moment functional belonging to the boundary. In general, it could be in the boundary, but not necessarily in a moment functional. So in the compact case, which is of interest in the moment here, we are in the nice case that we subtract the maximal mass and obtain a point in the boundary. And in the one-dimensional case, theory of Krein and Achieser, there is a theory of maximal masses, and it's shown that for moment functionals in one dimension, it exists always. How's the theory? I come back in a moment. From the one-dimensional case, truncated moment proportional interval without gaps. Each truncated moment functional has a representation measure where each point is a maximal mass. And this is not true in, this is much more delicate, let me say it like this, in the multidimensional case. And first, the definition, if we have a representing measure of a k atomic representing measure of the moment functional, x is in k in the semi-algebra x we have in mind, then it has, we say it has a maximal mass at xi if m is equal to the maximal mass. It's just self-explaining. And it has maximal mass if all atoms, the masses at all atoms are the maximal masses. If m sub j is equal to rho L xa for all atoms. So this is only at a special, at one atom, and here is for all atoms. And this is, turns out that in the multidimensional case, is a difficult notion. And I will relate it to another property called a positive separation property, PSP. If we have k points of the set, x1 to xk, and then we say this positive separation property holds if there are positive polynomials such that qj, xj is delta ij. Of course, if we have arbitrary polynomials, then we can have the square, which are positive polynomials, but it's not true because the square is in general not an A+. These are limited to a certain degree. So positive separation property is more than a separation property of polynomials. And this is related to a maximal mass property. If we have a representing measure, k atomic, and if these points satisfy the positive separation property, then the measure is maximal mass, and m sub j is rho L and kappa L. So the kappa L is the one obtained from optimization here. So if we get the solution of this optimization problem, then we get the maximal mass of this measure. It has maximal mass. And the converse, it's needed additional assumptions. One is that the set is compact, and then the infimum in this definition is attained. Just the other way around. Here we have infimum, and if the infimum, the minimum is attained, then we have can come back from maximal mass to obeying the positive separation property. So this, for instance, is true for inner points, or if the set is covariety. So in the multidimensional case, things are much more subtle. I will give in a moment a measure which is not maximal mass, again with a Robinson polynomial, but I don't know how to characterize or how to describe maximal mass functionals and so on in general. So for instance, I don't know if there's a truncated moment functional which has no maximal mass measure. And the Robinson polynomial is the main source for producing counterexamples because it has 10 considered in the projective space. We take for x a projective space, then it has exactly 10 projective zeros, T1 to T10. They are written here. And now we take the Robinson polynomial is non-negative and 3 variables and homogeneous. It's better than the Schmüdgen polynomial because it has 10 zeros. And if a polynomial, homogeneous polynomial in degree has 11 zeros, then it has infinitely many. 10 is just to break largest possible number before getting infinitely many zeros. And you will take a moment functional for a measure which has atoms precisely at this 10 zeros, and then we take another one. Another atom as a point which is not a zero. And then this addition makes it very different. This is maximal mass. It's determinate, then it must be maximal mass. And the covariety is just the zero set of the Robinson polynomial, these 10 elements. And adding this point, we get an interior point of the moment cone, and it's not maximal mass. Another thing for minimal functional is a theory of evaluation polynomials. And we take a positive functional again on a squared. L f squared is in the negative. Then I said it already, we can define a scalar product on the quotient of a times the kernel, given by this formula. And then the point for each point of the variety v sub l, the point evaluation is well defined and gives the linear function in a finite dimension Hilbert space. It's given by a vector. This is f tilde e tilde, and this is given by a polynomial. So there is a polynomial which gives the point evaluation. It's called the point evaluation polynomial. This is not unique. This polynomial, that's why I wrote here n, but the equivalence classes is unique. And then there is the following result. If K is the rank of the Henkel matrix, then there's a one-to-one correspondence between, bracket must be through, of orthogonal families of evaluation polynomials. This means they are different one are orthogonal to each other. And if we have the same one, then we get here a positive number. This is the norm. And let me write it in C(I) inverse, the inverse, and K atomic measures, and here is then the mass. So the K atomic measures are precisely in one-to-one correspondence with evaluation polynomials. And this function is then minimal. So the well-known theory from the one-dimensional case that evaluation polynomials lead to representing measures works in the for minimal functionals. I don't know how to get maximal mass measures. It seems to be very delicate, but it's possible to get measures what I called ordered maximal mass. I call such a measure ordered maximal mass if M1 is the maximal mass for the corresponding functional L. Then I take M1 away, and I call the functional then M-1. I take M1 away, so I start only with M equal 2. Then the M2 is the maximal mass of this second truncated moment functional. Then I take 2 atoms away and assume that M3 is the maximal mass for this corresponding functional. And this so I've written this here for M1 is a maximal mass for T1 at L equal L0. Then I take M1, the atom T1 away, so and I call this corresponding functional L1. M2 is the maximal mass of A2 and so on. And then it can be shown, it's not really difficult, that each truncated moment functional has a K atomic representing measure, which is maximal ordered mass. This has also a geometric meaning. We go with a functional to the boundary and then to a face and then to the interior of this face. Then we go to the boundary and again of the interior of the boundary of the boundaries of the faces and so on. So this always exists, but maximal mass seems to be delicate. And the reason, let me give one outlook of philosophy, truncated moment problem. If we look at the full multidimensional moment problem, the weighted sums of squares of polynomial play an important role, and we have the well-known interplay with Positivstellensatz and existence results, getting Positivstellensatz from the moment problem solution, and from the moment problem solution again the Positivstellensatz in the compact case. So this is the main central notion. In the truncated case, Positivstellensatz are not really useful, because the squares appearing in the Positivstellensatz, the degrees go up if you approach the polynomial approach 0, so we cannot apply the moment functional to this. So I don't think that it's useful again to use Positivstellensatz here, but there's another object from real algebra which enters into the theory in a very crucial manner: positive polynomials on the set, and their zeros play a crucial role. There are many points where this enters. For instance, positive polynomials are just the boundary hyperplanes of the moment cone. They enter into covariety. We take all polynomials, positive polynomials, which are annihilated by the moment functional. They enter in the theory of maximal masses, positive separation property. They enter also in the theory of Carateri-Tori numbers. The estimates can be obtained there depend on the number of zeros of positive polynomials. So in my opinion, this is the central the central algebraic question for getting results on the deeper results on truncated multidimensional moment problem. So it is true in the positive case if we use estimates on the number, for instance, from Petrovsky and Olejnik, to get estimates of the Carateri-Tori number. But we can use it also as I did it with the Robinson polynomial, to construct counterexamples, or examples where certain results from the one-dimensional case are not true. And the Hankel matrix method is in fact something which deals with squares only. That's why it seems to me it's very limited. There's a theory if we have a low-dimensional, only few atoms, then the Hankel matrix are useful. If we reach the opposite side, where we have a large number of atoms, then we get another theory. Okay, thank you very much for your attention. That's all.
Thank you for your talk on moments and different aspects. Do we have questions?
Yes, somebody is raising their hand.
Yes. Please go ahead. Unmute your microphone. So maybe I ask questions. So you look at this set of linear functionals positive defined on A square.
Yes.
And you say the evaluations are extreme rays of this code.
Moment cone, yes.
Yes,
but without squares is not true in general. It's very easy examples.
Yes, and so is there a way to measure so if you have say some extreme ray which is not an evaluation, do you have, do you know a way to measure the distance to the convex hull of the evaluation?
The distance of, say it again?
So you take the evaluations are these extreme rays of, some extreme rays of the cone, but
yes.
They are not all of them. Some
no, in case of L squared, of A squared, the extreme rays are precisely the point evaluations.
Yeah.
But for general sequence, for general vector spaces, this is not true.
So if you take an extreme ray, which is not an evaluation, and you want to measure the distance to the, say, the convex hull of spanned by the evaluations.
I don't know really.
I was wondering if this was the C of L, the L of X that you introduce.
But here in this case, it's I consider it on.
Yes, you just have one atom, but maybe if you look at the span of, give a finite number of atoms. The convex hull of this.
Oh, maybe no. Must be the moment function on A squared here. No, it's an A. It's an A. I don't know the distance to the one that's not. I worked only with point evaluations here, independent whether or not they are extremal. Then you come in the boundary and yeah.
So do we know about what is the type of these extreme rays here, which are not evaluations?
I mean, in the examples, in the interesting examples, extreme rays are precisely the point evaluations. But there are, if you take strange vector spaces, then there could be a cancelling. There could be a point evaluation which can be written as a linear combination of other point evaluations. So it's not extremal anymore. But if you take polynomials on of the degree 2n, then it's precisely the same point evaluations are extreme rays of the moment cone and vice versa. Each extreme ray is given by a point evaluation. That's a little bit tricky proof to the converse. It's the easy one, that the point evaluations are extreme. It's very simple, but the other one needs some arguments.
Okay. Yes. So, well, in the case where you look at Hankel matrices, so this are positive, say, positive functionals defined on A square.
Yes.
And then the X. So here X could be in a compact set.
Yes.
So here you have extreme rays which are not evaluations.
No, the other way around. Point evaluation could be a linear combination of other point evaluations. If you have only very few polynomials inside. I mean, this is not an interesting case. The point evaluations are the interesting thing because they enter in the moment theory and so on.
Yes, I understand, but there are also. I was wondering if there are other extreme points of this cone which are not point evaluation. And
yes, there are.
Yes, there are.
For instance, if you take the polynomials up to the degree 6, then we know they are positive. Then with the multiple polynomial, there are extreme points. Or I think of higher dimension, not only arrays.
And so
this is true for functionals and also for polynomials. There are functionals which are positive and not which are not extreme arrays.
So I was wondering.
I'm confused now, but I mean. But for the moment problem, this is a minor question because independent whether or not these are extreme arrays, I take always point evaluations because these are finite atomic measures and so on.
Yes, they are nice. Yes. Okay. Thank you.